I'm getting ready to transfer my RF generator and the low frequency generator, which you see here, onto a printboard circuit, something like this. Okay, and the goal is to make both fit inside this little plastic box I bought, which is not expensive at all. It cost less than $1. It's a soap box, and I intend to place the printed circuit inside like this, and in such a way that it leaves enough space to place a 9-volt battery next to it. So that's what I intend to do. So I'm going to transfer, as it were, the whole electronics onto the board, and then I'm going to leave enough space for the battery. Also, I want to make the generator work with several frequencies. I mean by that that I want to make it work at a number of fixed frequencies, like 450 kilohertz, 452 kilohertz, 455 and 457 kilohertz. If I can manage it, even 470, but I doubt it. Still, so I need to have the circuitry output, let's say 4 or 5 frequencies, fixed frequencies. So I'm going to use a rotary switch like this. Let me give you some more light. So I'm going to use a rotary switch like this, which allows me to select several positions, and that way I can make the generator generate fixed frequencies, and I will never have to tweak it again. At least I hope I won't have to. Obviously I'm going to use a 9-volt battery adapter, and I'm also going to build in an on-off switch to turn the thing on and off. I'm going to make it output a modulated high frequency at any frequency, output frequency, because, well, to have a pure signal, a pure 455 kilohertz carrier signal, for example, well, in this case, really doesn't make any sense, since the only thing I want to do is measure, or rather align IF circuitry with it. So a pure 455 kilohertz signal wouldn't do a lot for me. Also, I'm going to look for a piece of very flexible and preferably thin insulated cable, something like coax, you could say, to carry the signal out of the box and into the to align circuit. Also, you'll notice that I have copper tape, adhesive tape. Okay, this is real copper with an adhesive backing. And I have narrow tape and I have wide tape. Okay, so what I intend to do is, once I've mounted all the parts onto the circuit board, I will wrap some adhesive copper foil around it so as to insulate it from outside signals, or to prevent it to radiate signals outward. Obviously, since it's copper, I'm also going to solder it to the ground of the circuitry. Yeah, so I'm going to ground the copper insulation. So basically, I attached the print board to my little print board stand. As you can see, it's just a simple cast iron foot with some little grippers, which you can set in several positions. Now, I did that because it's much handier to grip the PCB with such a thing while you're busy arranging the parts. Now, before I start soldering electronic components onto PCB, at least a test PCB like this, I always try out the positioning of the parts first, just so that I know that I can get it right and use the minimal amount of space. Because remember, this is high frequency stuff. You have to keep the distances between the critical components, mainly the components in this corner, as short as possible. So that is exactly what I did. I played around with the parts until I got a placing with which I could live with, or that, well, at least satisfies me. You can also see at the bottom of the print board a whole row of small potentiometers. Now, each of these will be used to set a particular frequency. Okay, so the first one on the left will be for 450, the next one 452, then 455, 457, and I left one for which I'm not quite sure what its function will be. So either I will try to use it as a extra, to generate an extra frequency, so 470 kilohertz, or I might use it as a potentiometer for an external low frequency source, say another radio or a hi-fi or whatever, if I want to try out or experiment with transmitting music or sound in general. I'm not quite sure, I'm just toying with the idea. Okay, so then you see above the row of potentiometers a little bit of space left. So I'm going to try to use about half of the print board, so in an attempt to try to make it as small as possible. And that space above the potentiometers I will try to use for the low frequency oscillator. And if I manage, I think I can manage that, then I will simply cut the leftover print board away and I'll solder it, or rather I'll solder all the parts to it. Now, I don't know if you can see that, but let me zoom in. You see the transistor surrounded by, well, I think you would call it gold-colored foil. What it actually is a little bit of the adhesive foil, which I showed you at the beginning of the video. And I wrapped a little bit of the adhesive copper foil, just a tiny bit, around the body of the transistor to give it a shielding, as it were, to avoid unwanted radiation, high frequency radiation. Ultimately, I'm going to attach or connect the copper foil around the transistor to ground, yeah, to give it a proper shielding. Also, I'll put some extra copper shielding along the bottom of the print board once I'm finished, and I'm going to put copper shielding on top once I've aligned the circuitry. So once I've set all the little potentiometers you see to the correct position, to the correct frequency, I will cover the whole high frequency part at least with copper foil to provide enough. I installed the low frequency oscillator as well. As you can see down here, this part here, this is the low frequency oscillator, and well, it seems like I managed to fit it quite nicely and snugly into the space that was left over after mounting the high frequency part. Now there are still quite a few wires to be connected, but I'm well on the way to do just that. So hang on for the next update. I wired up the low frequency oscillator to my power supply, and as you can see, it's producing, well, 9 volts, a little bit less, maybe well, 40 millivolts less, but we're close to 9 volts. And I hooked it up to the power supply, and I also hooked up the output of the low frequency oscillator to my oscilloscope. And there you go. It now produces 201 Hertz, and it's quite stable too. So soldering the parts up on a PCB and making the leads as short as possible does help to make the signal pure. And as you can see, the signal is really pure and very stable now. So the conclusion is, at least for the moment, that the low frequency oscillator works, and works like it should. By the way, you notice that the frequency well, hasn't quite doubled, but I raised the frequency of the low frequency oscillator to 201 Hertz by dropping the resistor values connected to the base. So on the schematic, if you look at the schematic, the values of the resistors R2 and R3 are now 1.2 kilo ohms instead of 2.7. So if you're going to build a similar oscillator, you should use the value of 1.2 kilo ohms instead of 2.7. Okay, so so far so good. Now I have to wire up the multi-position switch up to my high frequency oscillator, and then I have to well, you could say I have to align it. I have to align each and every pot so that it generates another frequency as I turn the switch over. So that's the next step. I'm soldering up all the wires into one wire loom which will ultimately be connected to the multi-position switch. Yeah, so and I'm doing it step by little step. So if I take a pointer, okay, hang on. Okay, so you can see where I made the connection. So here is white, this is yellow, this is red, this is blue, and now I have only one to finish, which is the black one over here. So I'm going to solder up this one. Then the gray wire you see here, this one, is the common. So this goes really to the base of the high frequency transistor. So that's where I'm at. So we're getting close to the point where we have a completely wired circuit, and then we'll go ahead and test it. By the way, this is only a mock-up of what the design will ultimately be. At least once I'm certain that the high frequency part functions. So what I'm trying to figure out now is how long the wires of the wire loom should be, so as not to take too much space and not to be overly long to connect to the rotary switch. I also put temporarily a on-off switch into it and a battery, a 9-volt battery, so as to figure out the positioning of the parts. And as you can see, it fits rather nicely. Also, the output of the PCB or the high frequency circuitry will be through a BNC connector. So I'm going to build in a BNC connector into the box, and that will give me a lot more flexibility on the type of test wiring I want to connect to it. So yeah, I'm going to output the RF signal via a BNC connector. I'm also contemplating building in a very small LED which will light up if when I switch on the RF generator. Although I'm of two minds doing that, because well, the LED will consume, since it's a small LED, will at least consume 8 to 10 milliamps, and that will of course shorten the life or the amount of power the battery can give to the circuit. On the other hand, of course, if I don't have an LED and I forget to switch it off, it might keep on running and running and running without me knowing it, and then drawing all the juice out of the battery. Okay, I hooked up the rotary switch to the wire loom leading to each individual potentiometer, and I also hooked the RF part of my RF generator up to the power supply, and as you can see, it's getting very near to 9 volts. Now my intention is to align each potentiometer so that when I turn over the switch, the rotary switch, I get another IF frequency on the output. And as you know, I will output the signal through a BNC connector. But later I will talk a bit more about that. Anyway, the color coding is from light to dark. So white, yellow, red, blue and black. The gray wire is the common. Okay, so what I intend to do, and I'm going to try it live, is to align it to 450, 452, 455, 457, and then I'm going to try 470, but I'm not certain. So I'm going to do one of the potentiometers live, and then I'll do all the others, and then I'll show you the result afterwards. Okay, so let's try to align the first potentiometer. Okay, I'm in position 1, so here we go. So we're trying to get 450 kilohertz. No. 450. Oh dear. That is not so good. You seem not to be getting higher than 416. Let's try another position.
Mr. Speaker, I'd like to move that leave be given to bring in a bill to make an offence to operate a public service vehicle with tyres that are 10 or more years old. Mr. Speaker, there are plenty of other rubber-related products that people would be rightly cautious about trusting if they were decades old. So why would anybody trust their safety?
Okay, so hang on, I think I need to recalibrate one of the resistors. As you know, I finished attaching the rotary switch to the wire loom which comes from the print board. And as I was gearing up to start it, I noticed I couldn't get the frequency up to the desired frequency range any longer, unfortunately. So I was forced to examine what went wrong with the circuitry, and it dawned on me that when you start to attach all the wiring you see, let me take a pointer, that will make it a bit easier. So all the wiring you see here, going from the wiring loom which goes from the PCB to the rotary switch, all this adds extra impedance to the circuitry. And since we're dealing with high frequency here, it influenced the working of the oscillator, the high frequency oscillator. And therefore, with the values I originally used on the breadboard, I just couldn't get the desired frequency range any longer. I was sort of bound to the maximum frequency of 438 kilohertz, which in my case is useless. So I had to rethink a little bit the circuitry, and I finally came to the realization that what I needed to do was to change the 100 picofarad capacitor which I originally used in parallel with the impedance which you see here, the 470 microhenry. The 150 picofarad capacitor I used was simply too high. In other words, it was filtering out too much of the frequencies that I needed, namely all the frequencies in a rather narrow frequency band, say around the 450 kilohertz. So I started experimenting a little bit with smaller capacitances. So I used as a base 22 picofarad capacitors, which you see here, and I started with one, but that gave me still too high a frequency band. So I got a frequency band between 540 and 510 kilohertz, which was too high. So I added 2, and then the frequency was starting to lower. And I did the same thing 3 times, and then I finally fell into the Goldilocks zone of the 450 kilohertz. And indeed, it is now generating 450 kilohertz. Exactly. And as you can see, the wave is extremely stable now and pure. It's absolutely pure sine wave coming out of it. Okay, a couple of remarks. So, you know already that if you're going to attach quite a bit of wiring to your print board, and in combination with a lot of potentiometers as you see here, it is going to change the characteristics of your high frequency, of the high frequency part of the design. So the high frequency oscillator will probably drop in frequency. Okay, next you will have to experiment a little bit with the capacitance which is in parallel with the coil to get the right frequency band you really desire. Namely, well, in this case, since it's an IF tester, around the 450 kilohertz. Mind you, the maximum and minimum frequencies that you'll get out of this circuitry will never be more than roughly 40 kilohertz apart. Okay, so you have a rather narrow band of about 40 kilohertz. So choose wisely when you use a capacitance here. Also, it's quite clear that wrapping the transistor in copper foil and then grounding it did help for stabilizing the circuitry. And as you can see, when you watch the screen, when I move a metal part over the transistor, it absolutely doesn't influence the transistor, the oscillator at all. So I can even touch it. See, I can touch it, and it still doesn't influence the output. So that's perfect. Okay, another remark is that the maximum voltage I can use as a power for the power supply to supply voltage to the circuitry is 6 volts, a little bit more, say 6.1 volts. So I will need to use a sort of a regulation on the power supply of the print board. And in this case it'll probably amount to just using the correct Zener diode to regulate the voltage to the print board, which isn't really a problem. Okay, lastly, I attached a BNC connector to the output of the print board, as you can see over there. Now, obviously, I'm going to shorten the wire a little bit, and I'm also going to attach the ground of the BNC connector to the ground of the PCB. But basically that is the setup. And as you can see, I'm picking up the signal of the oscilloscope right at the end of the BNC connector. Okay, now there's one more thing I want to show you, and that is the amplitude modulated signal that comes out of the circuit. Let me set up the camera here. Okay, one more detail. When I switch over the rotary switch, I can change the frequency that is being output, as you can see. Unfortunately, like I said before, it also drops the amplitude a little bit, which is, I admit, a little bit annoying, but well, you know, that if that is the price to pay for having a multi-frequency tester, well, so be it. After all, it's not a very complex circuitry, and had I found a way to do some automatic gain control, well, gladly, but that would have made the circuitry a little bit more complicated yet again. So no, I'm going to leave it as it is, and I'm going to take the amplitude diminution, the amplitude attenuation for what it is. Okay, so the wave you see now is a pure sine wave, okay? And right now it's 450 kilohertz. Now I'm going to add or to overlay the signal with a 200 hertz low frequency signal. So I'm going to modulate its amplitude. So here we go. Hang on, because it's a bit dark. There you go. And that's the amplitude modulated signal. And you see the waveform, the basic waveform, you still see it. And then you see in between the waves, you see a sort of a shaded green area. Well, this shaded green area is the amplitude modulation of the signal. And as you can tell for yourselves, the signal is still pretty stable and pure. So actually, I think I can call the circuitry done. So all I'm left to do now is to build it into its little enclosure, which is the plastic box I bought for it, yeah, and build it in with the battery and all, and then give it a final go just to show you how it works once it's completely finished. Okay, so on to the last step. I connected up the RF generator to the power supply through the milliamp measurement position on my multimeter, and you can see when it's working, and it has a small LED on top of it, yeah. While it's working, its power consumption is 36.4 milliamps. Okay, so now I'll connect the low frequency generator to the power supply as well. And as you can see, the power consumption jumps up by 0.2 milliamps. So we could say that the total power consumption with LED is 36.6 milliamps. I'm using self-adhesive copper foil, as you can see, and I'm in the process of sticking a piece of copper foil down at the bottom of the box enclosure in which I'm going to mount my little RF generator. Now, as you can see, what I did was actually to peel off the one end of the copper foil tape, and I glued it to its correct place in the box, and then I'm gently peeling off the copper foil by pulling the backing of the foil along the part in which I want to glue it down, you know, and gradually, as I'm pulling off the protective backing, I'm gently pushing on the copper foil so that it sticks to the bottom of the box, yeah. And as I go along, I just pull a little end and rub it down, pull a little end and rub it down. And in the end, that's how it ends up. So that's what I'm going to do now. Okay, now I mounted the BNC connector, and you see I also put copper strip or copper tape on the inside, and it looks nice. Okay, some of you might think you've seen better, but well, this is only a personal little project, so it doesn't need to be really aesthetic for me. It just has to look sturdy, solid, well, be sturdy and solid and be practical, and that's it. So and here it is, finished, the whole RF generator, and as you can see, it truly is not bigger than a goodly cigarette pack, and you could carry it in your pocket if you really wanted to. So I decided to place the rotary switch slightly to the left of the cover and more at the bottom of it, and the on-off switch I built in on the right, and the on-off switch for switching the low frequency generator on or off on the left. So I mean, on the right is the on-off switch for the whole circuitry, on the left is the on-off switch for the LF generated, so the low frequency generator. I also built in a tiny blue LED into the box, so when I switch the whole thing on, the LED lights up. And a nice thing about it is, since the case is translucent, the LED also lights up the inner part of the top cover, which means that when I'll stick some decal symbols on top of it, I will be able to read them even in the dark. So yeah, it's a nice little design, and it was really built on the cheap. So I actually built it with the cheapest of the cheapest parts I could find. Because, as you know, my goal was to build something cheap, simple, and reliable. And the first two things, simple and cheap, are a fact. Whether it is truly reliable, well, that we'll see as we try to use it. So there's two things left to do. First, I need to align each of the potentiometers on the print board, on the PCB, which you see down there, and so that I can simply select the frequency with the rotary switch that I want to output. So remember, it's 450, 52, 57, and maybe 460 or 70 kilohertz. Also, once that is done, I will need to test the whole thing on a radio ultimately. So I won't do that in the weekend project update. But as you all know, I'm working on radios too, and quite soon I will take the opportunity to test this little IF alignment tool or RF generator to try to align a radio I'm restoring. Okay, so you see I'm powering it with a 9-volt battery, and oh yeah, I also built in a 0.1 microfarad capacitor in series with the radio frequency output. Quite simply because I want to make sure that no DC could ever enter the circuitry via the RF output. So yeah, and all in all, for a weekend project, it was really a nice little project to do. It's really fun to do, and especially if it works. So well, the next thing I'm going to do now is align each of those potentiometers you see down there, and then simply connect it up to my oscilloscope and see whether the whole thing works as I intended it to work. I hooked up my RF generator with a pigtail BNC connector cable to my oscilloscope. Now, aligning, mind you, with tiny little potentiometers as there are inside is not extremely accurate, okay? So if you're really patient and you take your time to do it, you can actually align up to, say, 1 kilohertz. Maybe if you're lucky, half a kilohertz, but that's really the maximum precision, yeah, that you can get out of it. I don't think you can do it more precisely unless you would use multi-turn potentiometers, but as we all know, multi-turn potentiometers are also much more expensive. And remember, one of the goals of making this project was to keep it simple and cheap. Okay, so there is one little detail that I omitted in my weekend project video, and that is that when you connect both oscillators to each other, well, you have the low frequency oscillator, which is the multi-vibrator, and you can tap the signal at either collector. It doesn't really matter which one, only remember that the phase is completely reversed at this end in comparison to the other collector. Okay, so it's a 180 degrees phase shift between both. Yeah, but the shape of the signal is completely the same. Okay, it's completely the same. So you take the output of the multi-vibrator at either collector, and then you inject the signal right, let me take my pointer, if I can find it, yes. So you inject the signal right there at this point. Yeah, and that way you will modulate the high frequency signal with the low frequency signal from the multi-vibrator. Okay, I suppose you could put it before a potentiometer, and then you could theoretically attenuate the signal a little bit too, but well, frankly, I wouldn't do that, because that might induce all sorts of noise and all that. So I, for my part, inject the signal right here. Now, as you know, I'm feeding the circuit with a 9-volt battery, which works perfectly. And I feed both circuits, so the multi-vibrator and the Colpitts generator or Colpitts oscillator, with 9 volts. And I switch them on and off with separate switches. Okay, so the multi-vibrator output is permanently attached to the input or to the base of the Colpitts high frequency generator, but the plus voltage of the multi-vibrator, yeah, is attached to a separate switch. In fact, it's the switch on the left here. The switch to switch on or off the high frequency oscillator is the one on the right. Okay, aside from what you can see here on my schematics, which I'm showing to you right now, there is one little detail that you will need to find out, I'd say, experimentally. So if you look at the Colpitts oscillator schematic, you see this capacitor here, yeah, a CT. Now, originally, when I had built the circuit, it was built on a breadboard, and probably due to all sorts of resistances and impedances and all that, the 150 picofarad capacitor worked fine. Once I built the high frequency oscillator onto its own dedicated PCB, the value of 150 picofarad was not good anymore. Yeah, especially after I connected up the rotary switch with all its separate little wires. as you saw before. Yeah, so if we open up the RF oscillator, well, you can see there are all these little wires going to the rotary switch. I tried to keep them as short as possible without being too short, because I still need to be able to service the circuitry. But these little wires all add extra impedance to the whole circuitry. And they also, of course, act as tiny little antennas and all that. So you have to be really careful, yeah, because this is a high frequency design, and it's a very, very sensitive to all sorts of capacitances, resistances and impedances that are floating about. Yeah, like little wires or leads, component leads, which are a little bit longer or shorter. So you really need to be careful. Anyway, one of the consequences is that the 150 picofarad capacitor, which originally functioned perfectly, was really not sufficient any longer. So, or I would say the value wasn't correct anymore. So instead of 150 picofarad, I ended up with a value of half of it. So about 73 picofarad. And I did that by using a lot of tiny little capacitors, and I think you can just about see them down there at the bottom. Yeah. So, and by retuning the circuitry as it is now, by using these little capacitors, I managed to bring back the high frequency oscillator into the range that I originally intended. Okay, so let's end up by showing you how it works now that in its box, and it's connected up to my oscilloscope. Okay, let's switch on the high frequency. There you go. So if I turn the rotary switch, you can see the signal change. Okay, so sometimes the change is tiny, sometimes it's a little bit bigger. Now remember, I told you that one of the consequences of using those little potentiometers is that the amplitude of the output signal does change a little bit. Yeah, so right now it's at 2 divisions and 2 volts per division, or 1 volt. Let me see. Yeah, it's at 1 volt per division. So you see, at 450 kilohertz, it's 1 volt per division. A little bit higher, it's a little bit more, I would say almost 2.5 divisions, so 2.5 volts. A little bit more and more still, you see? So it steadily climbs into the direction of 3 volts. Yeah, but that's about as far as I can push it. Okay, so now let's switch on the low frequency oscillator. And there you go. Now what you see is the amplitude modulated signal. Yeah. So there's a 201 Hertz signal superimposed on the 450 odd kilohertz signal. Yeah, and you see it's amplitude modulated. So it's that dirty green band you see around the shape of the signal. Okay, so it's that's the pure signal, that's the modulated signal. Okay, so yeah, you can also see that the modulation tracks perfectly the output frequency. So all in all, taking into consideration that it's a very cheap, very simple design, it is quite stable. So I'm curious to see whether it will function as intended when I will try to align a radio with it. Anyway, even if I don't, it was really fun to make. I learned quite a few things, and it didn't cost me that much money, and I can still use it for other purposes, so I can still repurpose it if I ever wanted to, by simply changing the 73 picofarad capacitance around the coil. I can push the tuning of the RF generator up to say 530 kilohertz or something like that. So I could still use it to test simply the tuning of a radio, not the alignment but the tuning. Okay, well, that's it, guys. I hope you enjoyed this slightly longer weekend project of building a IF alignment radio frequency generator.
This was because she had been the leader of this movement in Celtic for 10 years, at a time when it was criticised because paedophiles had penetrated